Hello everyone, welcome to Sulfur's classes. This is Tushar Shaw, and in this video we will be continuing to solve the UPSC CS main 2020 paper that we were solving since the last 12 videos, I guess. Okay, so in this video we will be starting from question number 6C, 6C. As the up till question number 6B we had already done in the last video. Okay, so the topic the topic related to this paper, that is the subjective type paper. I am not explaining it to you anymore because I already mentioned in every video in the line this series about how to solve a subjective type question, because normally we are like habituated in solving multiple choice questions, objective type questions for the rest of the competitive exams. Okay, so let us without wasting any time discussing that, let us directly dig into the questions that are given to us. So yeah, let me read out question number 6C. It says that a spherical soap bubble of volume pi by 6 centimeter in centimeter cube. So volume of the bubble is pi by 6 centimeter cube. Uh, is suspended in air. If the interfacial surface tension of the soap air interface is 27 dyne per centimeter. Okay, so the surface tension is uh, 27 dyne per centimeter. Okay, so calculate the excess pressure inside the bubble. So we have to calculate the delta P, that is the excess pressure inside the bubble. Okay, so the formula for excess pressure is given as delta P is equal to 4T by R for a spherical bubble. Okay, spherical bubble. Here T is the surface tension, which is 27 dyne per centimeter inverse, and R is the radius of the bubble. Okay, so we don't have the radius value, we have the volume, the value of the volume of the spherical bubble. So let us calculate the radius on that. Okay, so volume of a spherical bubble is this. So we know that volume of a sphere is equal to pi by sorry, let me write the formula first. 1 by 3, I'm sorry, not 1 by 3, 4 by 3 pi r cube. Okay, and the value of the volume is given to be, just scroll this down first. Okay, so the value of the volume is given to be pi by 6 is equal to 4 by 3 pi r cube. Okay, so pi is cancelled out. This 3 is cancelled out, giving 2, and this 4 is taken over there. So r cube is equal to 1 by 8, or r is equal to half centimeter. Okay, putting the values of the half, that is equal to 0.5 centimeter, we put the value in the above formula. So delta P is equal to 4 into the value of surface tension is given to be 27 divided by uh, divide by zero point 0.5. Okay, so let us calculate this value. Is the calculator. So 4 into 27 divided by zero point 0.5. So this is equal to 216. Okay, now this one will be in the unit, will be in the, here it is dyne centimeter inverse, and here it is also centimeter. Okay, so this will be moving out to dyne centimeter minus 2. Okay, obviously you can convert this into SI, but I am keeping it like this because no conversion or no mention is there for calculating the value in any SI unit. So we will be keeping it as it is. Okay, just the calculation and the formula must be correct. Okay, so let us move on to the next question. That is question number 6D. Okay, so question number 6D says that we have to arrange, sorry, not arrange, we have to derive the Maxwell's relation. The formula that we need to derive is del S divided by del P at constant T is equal to del V by del T by del T at constant P. Okay. So for this we need to firstly understand the concept of free energy from here. Okay. So let me just let me just start the derivation for that. So from the free energy, from the second law of thermodynamics, we know that G is equal to H minus Ts. Okay, and differentiating this equation we get ds is equal to dh is equal to dh, I'm sorry, here dg is equal to dh minus tds minus sdt. Okay, now for a isothermal change, okay, for an isothermal change, let us say we have this sdt. Firstly, we have to calculate the value of delta H. Okay, so from the first law, this is from the second law of thermodynamics. From the second law. Now, from the first law, we know, from the first law of thermodynamics, we know that H is equal to U plus PV, or dH is equal to du plus pdv plus vdp. Okay, and obviously du from another equation from initially we have derived that derivation I am not going into. So we already know that du is equal to tds minus pdv. Okay, so we just put the value of du over here. We will be getting the value of dh to be equal to tds plus vdp. Okay, vdp. Now putting this value of dh in this equation, equation number 1, we will be getting the value of delta G from there. Okay, or delta G is equal to TDS plus VDP minus TDS minus SDT. Okay, so we cancel out the TDS terms over here, so we will be getting DG is equal to VDP minus I'm sorry, yeah, minus SDT. Okay, SDT. Okay, so this is the formula for delta G. I'm just writing it down again so that you may box it. So this is the value for delta G that is given to us. Okay. Now we can differentiate this value, the delta G value, in many forms. So two forms will be obtained. So the two equations that are obtained are delta G by delta T at constant P is equal to minus S, and delta G by delta P at constant T is equal to V. Okay. So these are the two equations that are obtained. Let them be named as equation 2 and equation 3. Okay. So from this equation, we may like all of them. First of all, you must consider that G, T, P, S, and V. All of them are state functions. Okay. All of them are state functions, and therefore they follow the Euler's reciprocity rule. Reciprocity rule. Okay. So from these two equations, from the equation number 2 and 3, from 2 and 3, if we like draw the Euler's reciprocity rule in the conclusion, then we will be getting d of d. Let me just write it down properly. ddp of dg dt at constant p will be equal to ddt of, this will be at constant t, dg dp at constant t dp. Okay, from the Euler's reciprocity rule, now putting the values from the above equations, we will be having minus of mm, so after that we may write it like that, like minus of, I'm sorry, let the minus be written on that side. So delta S by delta T at constant T is equal to minus of delta V by delta P, delta T at constant P. Okay, delta T at constant P. Okay, so this is the Maxwell for second Maxwell relation. Obviously, first, third, and fourth is not mentioned in the question to be derived. Okay, so this is the only derivation that we required. So this is the correct answer about how you'll be writing the question answer correctly. Okay. So moving on to the next question. Um, so the next question says that solid sulfur on heating in an open container melts, but solid iodine sublimes. Why? Okay. So the question number is 6E. It says that solid sulfur on heating in an open container melts. Okay. So when heating in an open container means the pressure in the system is equal to the atmospheric pressure. Okay, so pressure is equal to 1 atmosphere in this case. So why we are mentioning pressure, because this is a case of a this is a question of the part phase diagram. So we have to draw the phase diagram of both sulfur and iodine and check at 1 atmosphere pressure what kind of changes will be taking place when temperature is increased. Okay, so let me firstly draw the phase diagram for sulfur. Okay, phase diagram for sulfur. Okay, so we have pressure over here, we have temperature. So okay, so here would be rhombic, here would be monoclinic, here would be liquid, and here will be vapors. Okay, so rhombic and monoclinic, both the rhombic and monoclinic are sections state are obviously uh, the like different forms of solid. Okay, different forms of solid state. Okay, now what happens is at 1 atmosphere this solid, this would be going into liquid, and then after this, like this plot would be like kind of like this. So there, when you add temperature at this temperature, you will be seeing that at 1 atmosphere the state changes from monoclinic to liquid state and then gaseous state. Okay, so this is the case. Now what have so this is why, so on heating the and keeping the pressure at 1 atmosphere and then heating, we will be seeing that from monoclinic the state of sulfur changes from monoclinic to liquid state. Okay, and therefore it melts. Now let us draw the phase diagram for iodine. So the phase diagram for iodine. So we have pressure over here, we have temperature over here. Now, so this is the phase diagram for iodine. This is solid, this is liquid, and this is gas. So at 1 atmosphere, the triple point for solid liquid gas junction is not crossed. Okay. So at 1 atmosphere, directly from the solid state, if it increase temperature, directly the gaseous state, like this is the point where sublimation point. So if we cross this temperature, directly from solid to gaseous state will be formed. Okay. Now, in order to make the like melt the iodine, you have to increase the pressure and then heat the substance, so that the process of melting can also take place. Okay. So this is all about this video. We solved 3 questions which were very long, and I guess just two sections of questions are only left in this paper, and then we'll be completing it. Probably 4 to 5 videos more will be required, and then we'll be like completing the whole set. Okay, so let us end this video here then. I guess I'll be seeing you in the next video, so thank you for this video. All right.